right. So, okay, super excited to be back. We're going to jump right back into where we were. So we ended off right before the limit of a function. Last time we talked about one of the basic properties of what we're going to be talking about in chapter 2, which is called the derivative. So these are like lines that are what we call tangent to a curve. Just like in the old school way that if you learn it in the way you learn it in geometry, where you have different types of tangents. So this is an example of a line that's tangent to a circle because it only touches it at one point. Okay, so that was an important distinction in geometry. However, when we start talking about functions or in curves, right? Functions are curves geometrically speaking, right? Like they're curvy. Okay. If we look, this line is tangent at P, but it's not tangent to the curve because it hits it twice, as you can see. As I extend this line from P, it hits C again, and it could even hit it on the left side too. And yet we still call this line tangent at P, right? Because we don't want to say something so global, because a circle, it's nice. It's not a curve like as we see with the polynomial where it has n behaviors, or the ending is sort of doing something at the end, and it goes on forever, right? A circle is just nice and closed, and I don't have to worry about, and I can basically define what a line is tangent at. A tangent line at the circle is much easier to see. In this case, what we have to do basically with curves is isolate around the point. We want to close off a small little neighborhood. So if I just covered part of the line, as you can see, this will still technically be like by the definition of a line that's tangent in geometry. Okay, so that was last time. So now we're going to move on to what the limit of a function is. So this is going to help us with our algebra when it comes to sort of discussing how to find limits algebraically or with certain rules, and how to understand them in such a case, in such a scenario. So let's start in the beginning. So the limit of function, having seen in the preceding section how limits arise when we want to find the tangent to a curve or the velocity of an object, we now turn our attention to limits in general and numerical and graphical methods for computing them. So they were just referring to, if we look past, or the last section before this, where we had, in order to find what this line tangent to the curve at P, in order to find that, we have to use the concept of the limit. Essentially, if I have a point P, which is the one I'm trying to find the tangent point at, and I take a point that's a little to the right of it, called Q, on the curve, and I make the two lines. I join the two points with a blue line here, and essentially what I'm trying to do is I'm trying to make this Q start going towards P. So that's what you see in these pictures here. The distance between them is shrinking. So not only can you come at it from the right side, as I stated, there's no particular order, right? I can also start from the left and bring it to the left. That's actually an important, that's going to be basically critical in understanding what the limit is. Okay, so that's just a little hint for what we're about to study. So I have P and Q, and I'm shortening that distance from the right. And as you can see, as I'm bringing Q closer to P, you see that the blue line's getting closer and closer to the red line, the secant line, or the tangent line. And that's exactly what we're trying to do here. That's exactly what the limit is doing. So on the right side, it's approaching that line, and from the left side, it's also approaching that line. Okay. All right, so enough about 1.4. Let's move on to 1.5 finally, because that's exactly what I'm trying to do here. Okay, let's investigate the behavior of the function f, defined by f of x equals x squared minus x plus 2 for values of x near 2. Okay, so notice the language here, right? It's already sounding a little different, right, compared to like what we usually talk about. Near 2, approximating at 2, right? We don't really do that, right? In math, a lot of times like find x or find the missing, right? It's very concrete, very discrete. So we're doing something a little less discrete, right? This is like the main point of calculus. The following table gives values of f of x for values of x close to 2 but not equal to 2. Okay, so let's see. Okay, so what that just said was, so as you can see, we're plugging in points that are getting closer and closer to 2. 1, 1.5, 1.8, 1.9, 1.95, 1.99. etc., etc. And f of x, as we can see, when we plug in these x values, 2, 3.7, 3.997, they're approaching something, right? They're not just getting arbitrarily big. They're getting big, but it seems like a smaller amount each time. Now let's look at values that are closer to 2 on the right side of 2. So 3, 2.5, 2.2, 2.1, getting to 2.0001. 001, sorry. And if you look at the x values, the f of x values, 8, 4.3, 4.003. So on the left side, the number that was really, really close to 2, 1.999, f of x was 3.997, close to 4. Getting close to x on the other side, close to 2, 2.001, we get a value of 4.003. So when we look at this, it's kind of approaching it from below 4, and then on the right side, we're approaching 4 from the positive side. So that's actually a really huge point there, right? And so when we look at the table in the graph of f, the parabola right here, the values of 2, as you can see, are approaching 4. So it's this y value that's here as we're like getting x closer and closer to 2. So this is the idea of what a limit is, just like the approaching factor, or the number that's getting super close to it. So it's like you can see that what number is really close to it. You kind of get a feeling, right? 3.9999 or 4.000001. You're like, okay, it's probably going to be 4. And so that's what this idea of a limit is. Okay. So the way we express what we just did is we use this sentence here. We express this by saying the limit of the function f of x, which in this case was x squared minus x plus 2, as x approaches 2, right? So as x approaches 2 is equal to 4. So it's a statement, right? And the way we write that is like this. The limit as x approaches 2 of x squared minus x plus 2 is equal to 4. Okay? And so in general, we use the following notation. So this is the intuitive definition of a limit as the book is sort of describing it as, or introducing it as. Suppose f of x is defined when x is near the number a. Okay, so this means that f is defined on some open interval that contains a except possibly a itself. So that's kind of what I was saying before in 1.4, which I won't bring up again after this point. It's very beautiful how they interconnected, or basically like set up the foundation of this book. So like 1.4 is really leading into 1.5, right? Like those are like the fundamental ideas. So we're looking at a small neighborhood around that point I'm trying to find the limit of. What does that look like graphically? So if I draw a rough sketch, let's see, a very rough sketch of a function on the 2D plane. Sorry. Okay, so maybe here's a small piece of that function, right? I didn't draw all of it, so I just decided to only draw a small open subset of it. Okay? And so basically, I just want to know that if this is A, then I want to know at least that the values on the left side over here and the values on the right side over here are defined near it. Okay, so meaning no matter what point if I choose any of these x values around here and right here, that there's going to be y values there. But what the definition also says is that except possibly a itself. So I actually don't care about what the value is at a. As weird as that is, but it happens, right? We want to be able to understand this thing in the future called singularities or holes or asymptotes. It's where the function's just not defined, and we can do this with, geometrically speaking, with graphs of functions. And so when we want to understand the calculus behind them and the geometry and the curvature, all this beautiful stuff, then I need to understand that the limit doesn't necessarily need to be defined there, right? Just like with residues, with singularities, right? If we have like a horizontal asymptote, right, the function approaches that thing, but it doesn't actually ever equal to that thing. That's what an asymptote does. And so it's like a limit, same idea. Okay. So we write the limit as such, the limit as x approaches a of f of x, some function, Remember, f of a doesn't necessarily need to be defined. That's exactly what I was just talking about, is equal to L. If this is true, right, if we write this sentence, then we say that the limit of f of x as x approaches a equals L. So here, this is the definition of limit, or the intuitive definition, quote unquote. So what is the limit here? Well, if I say the limit, then there's two ways of thinking about it. It's on the left side, as we just introduced it as, it's the limit or the approaching factor. And in this equation, it's just going to equal to that number with whatever that is. Okay, so it's a double definition essentially. We can refer to it in two different ways. Okay, that's really important, right? It's going to be either understanding what the limit is, right, or understanding that it's a number. Okay. If we can make the values of f of x arbitrarily close to L, as close to L as we like, by restricting x to be sufficiently close to a on either side of a, but not equal to a necessarily. Okay, this is the idea of infinity being used in a small region. Okay, so we can think of infinity as very big, but we can also think of infinity as very, very small. All right. Okay, good. Notice that the phrase of x not equal to a in the definition of a limit. This means that in finding the limit of f of x as x approaches a, we should never consider x equals a. In fact, f of x need not even be defined when x equals a, right? That's exactly what we were talking about. So it doesn't matter. There could be a hole there, a missing piece. So it doesn't matter too much. So we don't care about what actually is the value at that. So that's, I guess I could see why that's confusing, right? We're talking about something that doesn't necessarily need to be defined there. But it's like all focused around that point, right? And yet what we don't want to do is actually, we don't even want to worry about the value at that point. And yet at the same time, we kind of do. It's like a weird back and forth. But it'll make sense as we go further along. It's going to make sense in context, what we're trying to use the limit for. That's why it's so strange, and that's why math happens to be strange like that in certain ways. It's why I think people find math so weird and interesting, and unique. But it's like, the way I see it, it's very interesting. It's like very cool. It's like, why is that true? It's kind of the mathematician in me. Like, I want to know more about why that we introduced it in this way, or we think about it this way. That's sort of almost paradoxical to the way we think about things intuitively, right? Okay. Let's see. So it looks like the chapter is going to go into talking about finding limits of functions. Of course, what we can do, right? So we're not restricted from not just understanding the value at that point, like actually plugging in x equals a. So we can actually do that. If we can, then it actually will be the limit of that function. Okay, so that's no surprise, right? The reason why we say need not be equal to a is because it might not be defined there. But when it is, we're actually in the clear there. We can actually just plug it into the function, right? If it's not a singularity, then I should know how to find the value, right? It's just when the function equals that. And so that's the power of it, right? It's the paradoxical nature, is because, well, if it's not defined there, then how do I find it? Well, you have to understand the limit. So that's perfect. All right. Okay, so next time we will talk about some crazy functions right here. Some classic, really interesting functions here that we see that where the limit is where it's the value, the function may be defined at a point, but it may not have a limit. So that's another interesting thing. Okay.